what we're going to do today is we're going to start talking about topology, but like very simple topology, very special case of topology. And describing what topology is a little bit difficult without you kind of having seen more topology. So like I said, we're going to do like a very, very special case of topology. We're going to do the Euclidean topology of R1, right? So we're doing a very special type of topology, and we're doing it in a very special place, which means it's very, very specific. If this sort of stuff interests you, you can take, for example, 237. So we don't offer that at UTM, but it is offered at St. George. 237 will teach you the Euclidean topology of Rn, right? So again, a very specific topology, but in a more general set of spaces now. 257 at UTM will teach you metric space topology. So it's a slightly bigger category of topologies, if that's the sort of thing that you're interested in. And again, you probably don't even know because you don't know what a topology is. Notably, 257 at St. George does not teach that, okay? St. George only does Rn, not metric space topology. And then 327 is like specialist point set topology. Like it is hardcore topology. It's a lot of fun. It's legitimately probably one of the most important courses you can take if you plan on doing any serious mathematics at some point in your life. There are lots of math courses that are purely optional, right? So for example, number theory. You should have a little bit of number theory in your life, right? Just so that you've got the flavor of it. It's a great, and classical number theory is a lot of fun as well. But the reality is if you want to go and do mathematics in the future, like say go to grad school or do even applied math research or anything like that, you don't need number theory unless you happen to be doing research in number theory, right? Sure, for our math specialists, because again, it's just about breadth, right? Like we think that you should have some exposure to that because number theory is kind of like the classical field of mathematics, right? People have been doing number theory for, 2000 years. Whereas topology is much more recent, right? Topology's history is only, maybe 150, 200 years old. So there's a sense in which number theory is really one of the old classics. And so there is something to be said about having to take it. But the reality is you don't have to take it at any advanced level. And if you don't do well in it, you don't have to worry because you're just like, yeah, whatever. If I don't study number theory, it'll never come up again. Okay, legitimately, outside of undergraduate courses, I never used a number theory fact other than like basic divisibility, right? So you don't have to worry about that. Same sort of thing. Like the reality is you could like not do analysis, right? So this is analysis 1 and 257 is analysis 2. And if you go and you take 357, it kind of starts again from scratch. That's what happens in third year. All the courses restart and then you start to do math the real way. If you didn't take third year specialist analysis and you didn't study analysis, you didn't do any research in analysis, you'd probably be okay, right? Same thing with algebra, right? If you didn't take third year specialist algebra and you didn't study anything that involved algebra, you'd probably be okay. And in fact, one of my good friends during grad school managed to get away with this somehow. Like he basically just scraped through algebra, chose not to write its comprehensive exam, and so did like PDEs instead or something, and basically never used algebra in his life and somehow was okay. So there are these fields mathematically that like as long as you're not going to do any research in them whatsoever, you're probably okay. Now I say this, algebra is pretty important. You should probably have some algebra in your life. I don't know how Dan did that. That was crazy of him. I think he kind of suffered for it. You should have some algebra. But topology, no mathematician can avoid, okay? Because topology shows up in every single field. It shows up in number theory. It shows up in algebra. It shows up in analysis. Topology is so quintessentially like the foundational field that you just have to know it. It's like knowing what a set is, right? Because really there's a set which point set topology is like the study of sets. And obviously every mathematical field involves that at some point. So you can't avoid it. Topology is really important thing. And it's crazy to me, for example, that we don't have at UTM a specialist topology course, right? Like we have specialist complex analysis, but which is totally useless, right? Like that's not a fair statement. Complex analysis is useful, but it's not as useful as specialist topology, right? Like it's not even close, right? Like the gap is insane. So So we're going to get kind of our first flavor of topology. And what you'll actually notice is that we've kind of, myself and the TAs, have been hinting at some of this stuff beneath the surface, right? So for example, in one of your tutorials, and this was actually going to be, I think, an assignment question, right? Was this statement of the preimage of an open interval is open, right? It's not necessarily an interval, but it's an open set. And that assignment originally I'd stated what an open thing was. That's topology. That's the sort of thing that we're going to do. So if that, if that tutorial question freaked you out, well, you're in for a rough time. But I mean, that's a fairly advanced thing. So we'll get there. Okay, so like I said, we're going to do very, very special case. But hopefully it piques some sort of interest in you and you're like, ooh, hey, this stuff is cool. Okay, so the first thing that I want to do is I want to say I don't want to use open intervals for things anymore. Open intervals suck. So I'm going to define something new, but it's really just an interval. So definition, if A is a real, let's say A and R are real numbers, and R is strictly positive, okay? No condition on A, but R has to be strictly positive. We define the open ball of radius R, right? That's why R has to be positive, because our radii are always positive, centered at A, to B, BRA is the collection of all real numbers such that their distance from X to A is less than R. And we're like, oh, hey, we've seen that before, right? Precisely when we're talking about, epsilon delta E sort of proofs, this is exactly the sort of thing that we talked about. And what you can think about this is, again, is, we've called them balls. And I think that when most people think about balls, they think of like 2 or 3 dimensional things. We're doing this in 1 dimensional. So they're basically just line segments. But yeah, I mean, if you actually figure out what the open ball radius R centered at A is, let's say note that, so we know that X minus A is less than R if and only if negative R is less than X minus A is less than R, right? If and only if A minus R is less than X is less than A plus R, i.e. that is BRA is just the open interval A minus R to A plus R, right? And again, we've played with that sort of stuff before. Now, every open interval can be written as an open ball. And the reason that I'm saying this is because basically I don't want to talk about open intervals anymore. I just want to talk about balls. Because the nice thing about talking about open balls is that you have the radius, right? So that radius actually ends up being really, really important because you have the center of your interval, and then you have the distance from the center of your interval to each of your endpoints, right? So that ends up being really, really useful. So let's just kind of also make a comment. So also note that, okay, somebody double check me here. The interval AB, what is that going to be? So that's going to be B minus A over 2, A plus B over 2, right? That open, pretty sure that open interval is that, right? And how did I do that, right? Like you've got your interval. Again, you can just check it, right? Like you could actually do the math, but I'm pretty sure we can just intuit it. So the center of this ball should be the midway point, right? That's A plus B over 2. And then its radius. Yeah, I mean, implicitly, if I write A comma B, I'm assuming that A is less than B. But you're right. Like we could say that if we really wanted to, but implicitly. No, I shouldn't need them both to be positive. No. I mean, this midpoint formula works regardless of what A and B are. Right? I just need that B is bigger than A. And this length here is going to be half the length, right? And so again, you can check like if A is equal to -1, here, let's maybe do an example and check. So let's take -1 to 2, right? So we should suspect that the midpoint should be what, 0.5, right? And the radius should be 1.5. And does that work out? So the midpoint or the radius should be 1.5. Let's just write that as 3/2. And then the radius should be 1/2, right? And look, it doesn't matter if they're both positive or both negative. That does actually equal the formula, right? So I got 2 minus -1 over 2 here, -1 plus 2 over 2, right? So the formula holds regardless of whether they're positive or negative. Okay, so what we've effectively shown here is every open ball is an open interval and every open interval is an open ball, right? So there is a bijective correspondence, right? Which is just the math way of saying these are the same thing. There's a bijective correspondence between open balls and open intervals. Okay, and what this tells me is that I can use these interchangeably, right? Anywhere that I had an open interval, I can now use an open ball. Anywhere that I had an open ball, I can now use an open interval. And I know that these two things are equivalent so that I can freely move back and forth between them, right? It doesn't make any difference whatsoever. But again, you're going to see that in terms of doing things topologically, being able to state things in terms of balls is much more convenient than being able to state them in terms of intervals, right? I mean, there are times when that's not necessarily true, but like 90% of the time, this is going to be true. Okay, are there any questions so far? All right. So if there's one thing you kind of take from this, it should be this. And you could basically take this to be the definition if you really wanted to. Okay. So if you want to, and this kind of conversation up to here was confusing, yellow rectangle is your friend. That is the definition of an open ball. Okay. So this is now going to lead us to another definition. So let's say let U be a subset of R. So a point A in U is 1, an interior point if there exists some R greater than 0, such that BRA, the radius is a subscript, BRA, is entirely contained within U. Okay, so an interior point, you are inside, like strictly inside of your set, if I can put a ball around you and you stay inside of that set, right? So if we were to sort of draw a picture here, here's our real line. Maybe our set U, let's maybe draw it in like blue or something. And, this looks like an interval, but, we could add some more parts to it. Like maybe there's a point here, and then another smaller interval. So we'll say that this point here is an interior point. And the reason that it's an interior point is that I can put a little ball around it that stays in the blue stuff, right? So the blue stuff is our set U. And then the green stuff is BRA. Does that make sense? So you are an interior point if I can put a ball around you that stays entirely within the set. Right, exactly. These are not interior points. That is a great point. So these are not interior points. Right? And Nicole, exactly, you hit it on the head, because any open, necessarily open balls are intervals. They have, a little bit of girth to them. And if you try and put an open ball around one of these kind of singular points, it's necessarily going to leave the set, right? You don't kind of have a choice for that. Same thing. Can anyone else identify a couple other points in U? Actually, so not other points. There aren't actually any other points that are in U, but here, maybe let me make this like a square bracket here so that we're including that endpoint. Yeah, sure. Adam, I know what you're kind of saying there, but exactly like the endpoints, right? The endpoints of these sorts of intervals, right? This thing here is also not an interior point. right? Because if you center a ball at that point, necessarily the left part of that ball is going to leave the set, right? So we can see, I think everyone's getting an idea of this, right? You're an interior point if you're like strictly inside the set and there's a little bit of room around you to move. And that's exactly what the ball is giving you, right? What this green open ball is doing is saying, do you have a little bit of wiggle space around you where you can kind of stretch out and not leave the set, right? So that's what an interior point is. Now I numbered this number 1, so obviously there's a number 2 and maybe more, but no, there's actually only just 2. A is a boundary point. Oh, actually, you know what? I'm going to change this definition up here just so that I don't have to do this differently for boundary point. I'm going to say a point A in R. Oh, that's green. Is an interior point if this is true, and a boundary point if for every R greater than 0, BRA intersect S is not empty, and BRA intersect the complement is not empty. Okay. And so you might say, well, like, hold on, what did I win? Like the fact that up here I changed A to being a real number instead of being in U, like, does that really change anything about interior points? And the answer is no. Interior points must certainly still be in your set, right? Because, you know, there's no way this will be true unless A is itself in U, right? So clearly interior points, let's say note, if A is an interior point, then A is in U. However, boundary points do not need to be in your set. Boundary points do not need to be in your set. Okay. Is that SC, Stephen? Oh, yeah, sorry. That's probably because I wrote it in a way that didn't look nice. So this SC is the complement. Oh, sorry. Yeah, U. Yeah, I don't know why I wrote. Okay, and this thing here, this is the complement. Does everyone know what the complement is? Everyone's okay? If somebody doesn't know, you should say something. I can just tell you what it is. Exactly. It's everything not in S. That's exactly what it is. Okay, so like I said, boundary points don't actually have to be in your set. And so, for example, right, this is also, well, here, I'm going to change this now from not being an interior point to being boundary points. Okay. And so again, we can see, like, you know, if you take the open intervals 0, 1, both 0 and 1 are boundary points, right? Even though they're not in the interval themselves, right? So we could say, for example, so if U is, say, the open interval 0, 1, then the boundary points are 0 and 1. Okay, and you can prove this formally if you want. Exactly, and Yonji, this is a great question. So let's say example. Okay, what are the interior points of Q? Okay, so you take the rational numbers as being your subset of R. What are the interior points? Ah, okay, so interesting. So Yvonne, let's think about it. So let's say you chose a rational number. Can you put an open interval around that rational? Ah, right, no points in Q, right? The interior points of Q is empty. Right? Q has no interior points because there's no interval that you can put around a rational number, which only contains rational numbers, right? Exactly. So the boundary points are boundary points, maybe is the right thing. So what's the boundary of Q? What is the collection of all boundary points? Every real number, exactly. Right? By exactly the same reason why there were no interior points, every real number, if you put an open interval around it, intersects both the rationals and the irrationals, right? We know that both the rationals and the irrationals are dense, right? So every single real number is the boundary point of the rationals. Okay, so both of these require proofs. I suspect that right now, hopefully you all have a little bit of an intuition. You technically have to prove these things, right? So try to prove these things. Right? And ironically, the proof for the rational numbers is actually easier than the proof for 0, 1. And the only reason why the proof for 0, 1 is kind of annoying is you have to do something like this, right? Like you'll, here, let me introduce some notation. So let me say just notationally. We write u int for the interior points. And then this like, I can write that better. It almost looks like a 2, but you kind of like didn't finish it off. It's like a curly D, right? That's what this is. This is the boundary points. So if you want to take the set of all interior points, you write, u to the like superscript int, and then the collection of all boundary points is this, partial sign, this curly D. Right? And the reason why u being equal to 0, 1 is annoying, let's maybe like, this isn't normally, I'm not going to do the full proof for you, but I'm going to show you just kind of why it's annoying. So let's say, for example, as an aside, what would you claim that if that 0, 1 int is? So you take this open interval, you claim that it is what? What are the interior points of the interval 0, 1? Exactly, it's the open, it is itself, right? So how would you do this? You'd be like, okay, fix some x in the open interval 0, 1, right? So you've got this point x hanging out right here. What should the radius, you need to show that you can put a ball around it, which stays inside of the interval 0, 1. What radius should you choose? Okay, sure. So, but what is that distance, Sultan? Can you write down explicitly? Okay, yeah. So it is going to be less than half. Beautiful. Yeah, Yvonne. And so Sultan, yes, yours works because you recognize that x, the way I've drawn x is that it's closer to 1. Yvonne, though, has noted that I actually just said x was an arbitrary point. So it actually could have been closer to the other side, right? It could have been actually closer to x. And then Yvonne, you don't need the absolute value because you know that x is between 0 and 1, right? And yeah, exactly. Same sort of thing, right? So what you're going to do is you're going to say set R to be the min of either x or like 1 minus x, right? So what you're doing is you're basically saying, how far are you from each of the edge points, right? And then take the smaller of those two distances and that interval will work. Well, now you have to prove that that interval works, right? So now you would say, so claim, right, BR X is contained in 0, 1. Okay, well, now you have to prove that, right? So you have to pick some number in BRX and show that it lies inside of this interval. This is a little bit of work. This actually is not trivial. And in particular, the annoying thing here is that you chose R to be a minimum, Okay, so like try this. So this was, for the record, this exact question was 2 years ago on their first term test. The question was, and it was an in-person term test. It was, this is the definition of an interior point. Show that the interior points of 0, 1 is 0, 1. Okay, this was term test 1, the one that they wrote, yeah, in 157. Okay, so this is something that 100% I expect every single one of you to be able to do. This was their first term test, like 3 weeks into the course, they had to do this exact problem. Okay, so you all should be able to do it as well. I don't think that there's any math here that's tricky or complicated. It's just reasoning and logic. And like I said, this isn't straightforward. It can be frustrating because you can see the picture, right? And you're like, yeah, obviously, according to the picture, this is obviously true. What do I even have to prove? There is work involved, right? You do have to do a little bit of work. So give it a shot, and then we can talk about it next week. Especially if you're stumped, like we can talk about it, and I'll show you how you'd make this argument. The proof for Q, though, is very easy, right? The proof for the rational numbers and the interior and their boundary all just follows from density, right? You can just say, hey, look, there's nothing in the interior because every open interval contains an irrational. Pick an arbitrary real number, take an interval around it. It has both rationals and irrationals. Boom, it's a boundary point, you're done. So ironically, the rational numbers, which seems like it probably is the harder set to do these sorts of proofs for, it actually ends up being the easier set. Okay, so give this a shot and see if you can do it. It's not that hard. Like I said, just requires a little bit of logic, right? A little bit of like reasoning through what has to be true. Okay, so this is now going to lead, you've probably heard us use these words before, and you were probably okay with them, but now we're going to like really define what this means, right? So definition. A set U in R is said to be open if every point in U is an interior point. All right, so that is U int is equal to U. Okay, it is said to be closed if its complement is open. On the other hand, U is closed if its complement is open. Okay. Now, something we have to be very careful about notationally here is that a lot of students assume that if a set is not open, then it is closed, and that is not true, right? So note, a set can be neither open nor closed. Okay. Okay. Yeah. So Yvonne, clopen is not what you want because clopen is both open and closed, right? So that is okay. But Sultan, your example is perfect. So for example, zero, one, right? Or Nicole, yeah, absolutely. We could do, and Nika, yeah, you're both absolutely correct. We could do something like, maybe 0, 1, union 2. Absolutely, right? Yeah, Stephen, the half open interval. All of these are examples of sets that are neither open nor closed, right? They definitely have some boundary points, which is bad because they're not all interior points. And in fact, we haven't proven this, but this is a nice little exercise for yourself. Prove that boundary points can't be interior points and vice versa, right? And intuitively, that's true. And the proof is pretty straightforward. But if you're an interior point, you can't be a boundary point. If you're a boundary point, you can't be an interior point, right? So let's just, say that out loud so that we know that that's true. And yeah, if you look at U, it's not all interior points, but its complement's not going to have all of its interior points either, right? Because, for example, if we took the complement of this set, we would get, negative infinity to 0 has a boundary, or has a, it's not an interior point, to 1 infinity. And if we took the complement of this set, this is going to be much less fun to write out. Right. And again, you can see there are a bunch of like things here that aren't interior points, right? And same thing over here, right? Not an interior point. Okay, that was pretty, I know probably nobody could read that. Not an interior point, like that, right? So yeah, there are sets that are neither open nor closed. Now, Yvonne, you kind of like had an idea here. Is it possible for a set to be both open and closed? Can anyone think of one? There's not a lot of them in this example. In Euclidean R, there's very few of them. Sure, R is exactly an example. R is both open and closed. Okay, let's think about that, because some people are like, wait a second, is that true? So I hope you all agree it's open, right? Certainly R is open, because if you take any open ball in R, it's also in R, right? So every point is an interior point. Okay, but to show that R is closed, we have to show that its complement is open. What is the complement of R? The complement of R in R. It's the empty set, exactly. Moreover, the complement of R is equal to the empty set. Now, is the empty set open? You know the answer is yes, because I've already told you that the answer is yes. But why is it open? Okay, but Adam, you have to be careful. So that ends up being a true statement, but that's not the definition of open, right? Exactly, Sultan, exactly. There are no points to talk about. So when we say every point in the empty set is an interior point, that's a true statement. Any statement that says for every x in the empty set, p of x is a true statement, right? Anytime you talk about all points in the empty set, the statement is automatically true. If you say there exists a point in the empty set, it's automatically false. But for all x in the empty set is automatically true, right? And this is precisely the notion of a vacuous truth, right? It is open vacuously because there are no points in the empty set. So yes, every point is an interior point. Okay? Is everyone okay-ish with that? So there's one other Clopin set. What's the other Clopin set? The other set that is both closed and open. No, Q is neither. Yvonne, right, the empty set. The empty set is also both closed and open, right? Because necessarily, if U is both closed and open, then its complement must also be both closed and open, right? So if you have a Clopin set, this is what Clopin is what you describe as being closed and open. If you have a Clopin set, its complement must also be Clopin, right? Just because it's, U is open and closed. And so its complement must have the dual properties, right? So if U is open, then U complement is closed. And if U is closed, then its complement must be open, right? By definition. So these things always have to occur in pairs. These are the only two clopin subsets of R. Okay, and there's a reason for that. It's a little bit hard to, I guess it's probably not impossible to prove. When you start to do more topology, you'll find other examples of clopin sets. You kind of have to change the topology around. There's a very natural thing in which we can actually use the Euclidean topology to get other non-trivial clopin subsets in R, in Euclidean R, like not even change the topology, but we have to talk about the subspace topology, and that'll be a game time decision whether I talk about the subspace topology. Okay, so is everyone okay? Everyone has an okay feeling for what open and closedness is? Okay, sweet. So far it's mostly been definitions, maybe a little bit of examples, so on and so forth. Proposition 1x, not x, R and the empty set are both open. Okay, we literally just proved that, so I'm not going to do it again. I didn't prove it. Maybe I talked about it. If UI is an arbitrary collection, and I mean arbitrary, of open sets, then the union is open. Okay, so this says an arbitrary union of open sets is open. And when I say arbitrary, I truly mean arbitrary. Okay, let's get rid of any misunderstanding here. I'm not saying finite. That's certainly true. Finite unions of open sets are open. I'm not saying countably infinite, right? I'm not saying that there's a U1, a U2, a U3, a U4. If we do that, if we've got a countable collection of open sets and we union them together, that's certainly open. This says arbitrary, which means that this indexing set, capital I here, right, which is just the set that we're using to keep track of the use of i's, that thing can be as big as we want it. Yeah, no, we don't even know that I is countable, right? I doesn't have to be countable. I could have the cardinality of the real numbers. We could have a U sub x for every x in the real numbers. And so there isn't a notion of consecutiveness in the real numbers, right? We can't talk about what it means to talk about the next real number. So yeah, when I say arbitrary, I mean completely and totally arbitrary. As many sets as you want, right? You could have a real number's worth of open sets. And when you union them together, the answer that you get is open. Okay, so that's kind of, let's disillusion ourselves of any misunderstandings right now. This is truly an arbitrary union. Okay. And I want you to start thinking about how you're going to prove this. There is a part 3 that I'm going to write down, but how would you prove that an arbitrary collection, an arbitrary union of open sets is open? The proof is trivial. There's almost nothing to do, but start to think about it, right? Like even draw some pictures if you wanted to. Like if you took a union of open sets, how do you know they're open? Okay. So Chiang, hopefully you got what you needed. So the complement of a set is open, then it must be closed. Yeah, exactly. Yeah. Okay, 3. If now, again, let's be careful. So if U1 through UN is a, no, not necessarily, because we don't know, Yuanji, that they union to give you all of R, right? Like you don't know that that's true. Right? In fact, you can do really weird things with open sets, right? Exactly. Finitely many intersections is open. Yeah. Okay. So finite intersections of open sets are open. and arbitrary unions of open sets are open. Okay, any questions? Jiang, I'm not certain if you have a question or not, because your last two comments are just H's and a period. So I'm not certain if there's confusion. Is there any confusion? Like, I'm happy to answer any questions. Let me know if there's something that doesn't make sense. Is an infinite collection of open sets open? You have to do something to them, Yvonne, right? Like you can't just, okay, oh, an infinite intersection, no. And so, okay, no problem. So everyone, this is a great question. So Yvonne is asking if an infinite collection of open sets is open. So first of all, it could be, right? This proof isn't an if and only, the statement isn't an if and only if. So it's possible that an infinite intersection is open, but you can't guarantee it, right? And so here's a good question. Can anyone think of a counterexample, right? Can you think of an infinite intersection of open sets or an infinite collection of open sets whose intersections is not open, right? So I want you to think about that. Meanwhile, I'm going to start proving this. So proof one, we already talked about. Okay, two. So here's what we're going to do. What do we need to do? We're going to take the arbitrary union. We're going to pick a point. We're going to show that that point is an interior point, right? So let's say pick some x in the arbitrary union. Okay. Since it's in the union, what does that mean? What does it mean if you're in the union of a bunch of sets? Exactly. Well, okay. So Marie, we don't know what is open. Like we don't know that the whole union is open yet, right? Like I'm trying to prove it. But Nicole, exactly. X is in one of the UIs, right? If you're in a union of a bunch of sets, then you must be in one of those sets, right? Because that's what the union means, right? Is that you're in one of the sets. So X is in U, I don't know, let's give it a special name. Let's call it UI naught for some I naught. In I, okay? But now UI naught is open, right? By assumption, we assumed UI naught is open. Is open. So there exists some R, right? So X is an interior point because it's in there. So there exists some R greater than 0 such that BRX is entirely contained in UI naught. And since BRX is entirely contained within UI naught, it must be in the union as well, right? So what have I shown? I've said if I pick an arbitrary element of the intersection, I can find a ball, an open ball that lives in the intersection. Namely, X is an interior point. Oops. And that proof is done. That takes care of 2. Does that make sense? Again, right, we're really leveraging the definition of a union. If you're in the union, you're in one of the sets. That set is open. So there's a ball that lives inside of you. Boom, you're done. Okay, so 3, we need to show that the finite intersection is also open. So let's do the same thing, right? We're going to choose a point in the finite intersection. So let X be in the intersection from I equals 1 to N, UI. Okay, what does it mean that you're in the intersection? Yeah, exactly. You're in all of them. Exactly, perfect. So X is in UI for all I equals 1 to N, right? Okay. Now, each of the UIs is open, right? So that there is a radius such that X, the open ball of radius of that radius lives inside of UI, right? Since each UI is open, there exists an R sub I, right? And that radius could be different for every ball. So there exists an R sub I such that BR sub I of X lives inside of UI. Okay, now I'm kind of stuck because I have a whole bunch of different radii that live inside of each of the UI, but I need one radius. So what radius am I going to choose? Exactly, take the minimum. Right? Because now we know that BR of X always lives inside of BRI of X. You know, we didn't prove that, but I think it's like, again, it's a one-line proof. If you have a smaller radius ball, it lives in any bigger radius ball centered at the same point, right? Like, hopefully that's clear, right? I hope that's okay. And BRI is in UI, right? So what have we shown? We've shown that this is in every single one of the UIs, and therefore it's in their intersection. So X is an interior point, right? And again, X was arbitrary. So we're done. Okay, right, so that's not bad, I think, right? Like, this is probably something that looks a little bit intimidating the first time you see it, but like, once you actually start getting around to proving it and you just use the properties of intersections and unions, you're like, oh, it's not too bad. Now, somebody tell me though, oh, BRI, right? So we knew, let's see, let me highlight it. So since each UI is open, then I know that there is some ball of some radius that lives inside of UI, right? So because I know that X is an interior point of U sub I, there's some radius R sub I such that that ball lives inside of there, right? Like, I'm just using the fact that each of the UIs is open to guarantee that I can put some ball around X which stays inside of UI, right? But each UI might have a different radius. So I have to just make sure that I call the radii different things. And exactly, yeah, if the intersection is empty, then you're good to go. Can we prove that the intersection is at least an open interval or the empty set? Actually, I guess that's true. You're right, Adam. I really should have said that. You exactly, yeah. Okay, good point. You caught me. You caught me cheating. If the intersection is empty, we're done. So assume it's not empty. But Adam, you are absolutely correct. If I were doing this on a test, I would have lost a mark. Right, so Adam, I think like hopefully that answers your question. It's not that we're proving it, we're saying it either is empty or it's not. If it is empty, we're done. So let's consider the case where it's not empty because that's the more interesting case. Right?
Can I talk?
Yeah, sure.
In fact, my question was more about, but like, imagine the intersection of like all these open intervals was like a point, like 0, but it's not possible. But we should prove it, no?
No, I mean, we've effectively already proven it, right? So what we've proven is if you can put a ball around every, like, so you've got this intersection of finitely many open sets. And if each of them are open, you can put a little ball around it, which has some width. And so that ball of that width must stay in the intersection as well. So it's impossible for it to be a single point. Like, right? Like this is what we've proved right here. You know, it's the end of the proof, but we've shown that this ball, this open interval must live in the intersection. And if this open ball lives in the intersection for every single point, right? Not just this particular X, but this X was arbitrary. So it must be true for all points. That means that every single point has a little open ball around it. So it can't have just intersected down to a single point. Does that make sense?
Yes, that makes sense. I didn't see it that way. Okay.
Yeah, no problem. But actually what you hit upon is exactly the right idea for the counterexample of, you know, what can happen when you take an infinite intersection, right? So if you take an infinite intersection, this breaks precisely because of this idea that you have that your intersection could actually collapse down and just give you a single point, right? So before we do that, and again, hopefully people were kind of thinking about that as an example. Hold it. Right, okay, so Stephen, this is a great question. Can anyone tell me where I used the finiteness property in the proof of three, right? Where did I have to use the finiteness? Where was it essential? So if I'd replace this with an arbitrary intersection, exactly. So what about the min? Like, why couldn't I just put inf there, right? Because I could put inf. These numbers are all bounded below by the number 0. No, it's true. We don't know the min, but why couldn't I take the infimum? Because the infimum would then be a smaller number than all of the radii that I gave, right? And we know the infimum exists because this is a set of numbers that's just bounded from and below. Why would the infimum not work instead? No, hold on. You're all thinking of different things. Let's check our types here. We're taking the infimum of the radii, right? Right, of the radius. So the radius doesn't have anything to do with being in the set or not. If on your set a wrong thing and then the right thing, and something exactly, what if the infimum is 0, right? So that's the issue, is that if you don't have a finite set, if you have an infinite set, then the infimum could be 0. And by definition, the radius has to be greater than 0, right? And I know that we're a little bit over time, but let me just leave you with this. Take the intersection from I equals 1 to n, or 1 to infinity, of, let's say, -1 over n to 1 over n, right? What is this intersection? Anyone? Any idea? Yeah, it's just the set 0. Right, and Adam, this was kind of, I think, what you were bringing up, right? Is that like it's actually possible for the intersection to shrink down. This is definitely not an open set. I think everyone agrees. So it has to be finite precisely because the moment you allow infinite, your intersection could actually shrink down. And it doesn't have to shrink to a single point. It's actually possible to take an intersection of open intervals and get a strictly, you know, a closed interval that isn't just a singleton. You could actually get a closed interval that has, you know, stuff inside of it. So the reason that precisely breaks, if you were to try to apply this proof, is that you couldn't guarantee that this number is positive, that the radius is positive. And you can see that that's exactly what's happening here. If you chose any point in here in the intersection of this set, in fact, yes, 0 is in each of these things and has a radius that works in each of these -1 over n's to 1 over n's. But the problem is that the radii that you need to take keep getting smaller. And so when I take the infimum, I eventually get 0, right? And that's why the proof doesn't work. So it has to be finite intersections for us to be able to guarantee anything. Exactly, Adam. So it can happen with infinity, but not with a finite interval. Exactly, because we proved that it can happen with a finite interval, and now we have an example where it can happen with an infinite intersection. Okay, everyone? Anyway, I went a little bit over. Hopefully that wasn't too big a deal. I think I really was super happy with like the engagement. You guys were really like contributing here. So that was a lot of fun. We'll carry this on a little bit more next week. I would really like to get to compactness and connectedness. I think that'd be a lot of fun and that a lot of you would enjoy that. So that's my goal. But that's going to finish it off for this week. I will post test information on Friday about what next the term test 3 is on, which is on December 3rd. So next Friday. So keep an eye out for that. Otherwise, get your assignment done. Have a good weekend. And I will see you on Tuesday or Monday if you come to office hours. No problem. Thank you, everyone. Nicole, I'm glad to hear it. Thanks, everyone.